based crypto. We have two talks. The first one is called Extractable Witness Encryption for KZG Commitments and Efficient Laconic OT by Niels Fleischacker, Matthias Andersen, and Mark Simkin. And Niels is giving the talk.
Okay. Yeah, thank you for the introduction. So we want to talk about extractable witness encryption for KCG commitments. So the first thing we could start with is a reminder of what witness encryption really is. So if we start with normal public key encryption, you have a key generation algorithm that outputs a key pair, a public key and a secret key. And you can use the public key to encrypt a message that results in a ciphertext. And you can decrypt that ciphertext with the secret key, and it should hopefully result in the same message. Now, witness encryption basically gets rid of the concept of the key generation, and instead, in a sense, uses like naturally occurring key pairs. We have like an NP relation, and we now use the statement of the NP relation as our public key, and we use the witness as our secret key. So the correctness and security of such a witness encryption scheme is the following, that if we have some pair XW that is in the relation, so X is a statement, W is the witness for that statement, then we can use X to encrypt the message, and we can use the corresponding witness W to decrypt the message again. We get the same message back. It's just correctness. And then we have the security guarantee that if X is actually not in the language, so if no witness exists, then any the encryptions of two messages, M0 or M1, are computationally indistinguishable. So this in particular means that this is only meaningful if you have a language where, well, there are some things that are not in the language. So if you now want to look at witness encryption for KCG commitments, so a KCG commitment, they look like this. Basically, we have the setup, which is you get all of these powers of tau in the exponent. And if you want to commit, so KCG commitments are polynomial commitments, so we want to commit to a polynomial. And what we actually do is we simply evaluate the polynomial f that we kind of want to commit to at the position tau in the exponent. We can do this because we have all of these powers of tau. And now if we want to open the commitment at some position, basically we define this new commitment, this new polynomial q, and we also evaluate this new polynomial q at the position tau, again in the exponent. And if we want to verify, well, we have this nice verification equation. And if this verification equation goes through, then everything is fine. Now, we can define a language for KCG. So basically valid triples of commitments, positions, and values. So basically this language is those triples of a commitment, a position, and a value, such that you can open the commitment at this position to that value. So that means there exists a pi such that verification equation holds. The problem now is that this is actually a trivial language. Like any triple is actually in the language because, well, you can define actually a pi for any such triple. These pi's are hard to find under certain hardness assumptions, but they do exist. So that means that normal witness encryption would not give us any security guarantee. So that is why we look at extractable witness encryption. Extractable witness encryption is basically to normal witness encryption what a proof of knowledge is to a normal proof. That means we define extractability in the following way. We say a witness encryption scheme is extractable if there exists an extractor such that for any adversary that can distinguish encryptions of M0 from encryptions of M1 with non-negligible advantage, then the extractor can actually extract a witness for X from this adversary with non-negligible probability. So this means now this is meaningful even if the language is trivial, because even if the language is trivial, finding the witness might actually be hard. And in the case of KCG commitments, finding those witnesses is hard as long as the KCG commitments are actually binding. So what we do construct directly is not actually extractable witness encryption. We make our lives a bit easier and instead construct an extractable witness chem. This is fine because it turns out that even for extractable witness chems, you can use the normal principle of hybrid encryption to basically get a witness encryption scheme afterwards. So you can just encapsulate a symmetric key, and then you can use a symmetric encryption scheme to then later get the encryption scheme from this. The proof is slightly more complicated than for normal hybrid encryption because you need to deal with the extraction instead of just indistinguishability, but it works fine. So we actually want to construct an extractable witness chem. Now, what is an extractable witness chem? Well, basically, we have an encapsulation algorithm that uses the statement X as the key, as the encapsulation key. And yeah, we basically encapsulate a key K and produce a ciphertext C, and then you can use the witness for X to decapsulate. And security definition is, again, extractability. That means that a witness chem is extractable if there exists an extractor such that for any adversary that can distinguish between encapsulations, between a ciphertext and the encapsulated key, and the same ciphertext and a random key with some non-negligible advantage, then the extractor can actually, again, extract a witness for X from this adversary. So how do we construct an extractable witness chem for KCG? For that, we can start by looking at the verification equation. The verification equation has two sides, and we can notice that the left-hand side is actually completely publicly computable. This is only basically based on the statement. The statement consists of the commitment, alpha and beta, and on the left-hand side, we only have those values. On the right-hand side, this is not publicly computable because it uses the opening, which is actually the witness. We might notice that actually the witness is also the only thing that's not publicly computable here. Also, the second part here is actually publicly computable. We will also make use of that. Now, the idea is basically that we now can encapsulate in the sense that the encapsulator can use the left-hand side to compute this value, and the decapsulator can basically use the right-hand side to compute the same value. Of course, computing this value is not actually that helpful because this is a deterministic value, so anybody could compute the key, so that would not be great. Instead, we actually re-randomize this value just by multiplying it with some random r. So now we have some random value s. We cannot directly use this as a key. Among other things, it's not like a random bit string. This is just some group element. So we normally want to have just a random bit string at the end, so we need to encode it somehow. But also the proof would not work like this because we actually need to extract from random oracle queries. So we apply a random oracle to the S to get our key K at the end. Okay, so now what is missing is the ciphertext. We need a ciphertext that we send over to the decapsulator that the decapsulator can then use to derive the same key K. And as I already said, the second part of the right-hand side is actually also publicly computable. And so what the encapsulator can do, it can compute the second part of the right-hand side, and it can multiply it by r. And once we do that and send this to the decapsulator now only needs to pair their own opening with the ciphertext And what we will end up with is exactly the right-hand side of the verification equation multiplied by the R. Because of the bilinearity, it makes no difference where we multiply the R. And so then the decapsulator can re-derive the S and can then apply the random oracle to get the key K. So that means we now have basically our chem. Now, proving extractability for this is not that straightforward. Basically, we need to assume the L-D-log assumption, which is the basically variant of the D-log assumption, where you're not only getting tau in the exponent, but you're getting all these powers of tau. And it should still be hard to derive tau from this. This is a relatively strong assumption, but on the other hand, it's the same assumption that you're already making if you're using KCG commitments. You have to use KCG commitments anyway to basically make use of our scheme here. So this is not like an additional assumption that you need to make here. So I will not have time to go through the details of the actual extraction proof, but we do prove the extractability in the combined algebraic group model and random oracle model. The basic idea of the proof is that whenever an adversary is capable of distinguishing between the real key and the random key, that means that they must have made a random oracle query to this value S that gets basically sent to the random oracle here. This is just necessary because otherwise they would not be able to distinguish at all, because from the point of view of the adversary, both keys are truly random as long as this query is not made. And once this random oracle query is made, then we rely on the fact that the adversary is algebraic, which means it needs to explain how it generated this value that is sent to the random oracle. And from this explanation of how this S was computed, we can then actually extract an opening for the commit. Now, why would we actually want an extractable witness encryption for KCG commitments? Well, there may be many reasons, but one particular example of an application that we constructed in our paper is laconic oblivious transfer. Now, what is laconic oblivious transfer? So most of you are probably familiar with normal oblivious transfer. This means that we have Alice on the one side, she has two messages. We have Bob on the other side, he has a choice bit, and they communicate. And at the end of the communication, Bob should output the message MB, so the message that corresponds to his choice bit. And he should not learn anything about the other message, and Alice should not learn anything about the choice bit at all. Now, what makes an oblivious transfer laconic? Well, in a laconic oblivious transfer, Bob does not just have one choice bit, but from the very beginning, he has a large database of many choice bits that he basically commits to in his first message using a short digest. And after this initial digest, now Alice can basically send a single message for her first pair of messages to Bob, and Bob will learn the message that corresponds to his first choice bit. Then Alice can just send a second message that corresponds to her pair of two messages of the second two messages. And Bob will learn the one corresponding to his second choice bit, and so on and so forth. So all of this communication needs to be short. So it's much shorter than linear in the database size. So this means using a laconic OT, you can actually make many OTs with very little communication, as long as it's possible that Bob will basically commit at the very beginning to all of his choice bits. So how can we get laconic OT from witness encryption? Well, we have a setup for laconic OT. There we will basically just use the setup of the KCG commitments. And we'll use the KCG commitment as a vector commitment here, which basically just means we commit to a polynomial that corresponds to the entries in our vector at the positions like 1 through whatever the length of our vector is. And so this function, this is the algorithm H here. This is basically what Bob uses to compute the digest at the beginning. So basically his commitment to his database. And there he basically just commits to the database using the KCG commitment. And then he directly batch opens all of the positions of the commitment. This is just done because it's much more efficient than individually opening at a later point. And once we've done that, then Alice can send her short messages that correspond to her 2 messages in every step of the laconic OT. And what she does is basically just she encrypts her 2 messages using 2 contradictory statements. Basically, the first ciphertext is of M0, encrypted towards the statement that the digest can be opened at position I to value 0. And the second ciphertext is of message 1, encrypted towards the statement that the digest at position I can be opened to 1. And these are contradictory statements. So because the adversary should not be able to, or the recipient should not be able to open the commitment to 2 different values at the same position, that just would contradict the binding property of the commitment scheme, it should be impossible for the recipient to learn anything about one of the 2 messages. And on the receiver side then, the receiver basically just checks in his database what his bit is and just decrypts the corresponding ciphertext and thus learns the message MB. Yeah, so this is the laconic OT. It is a very efficient laconic OT. So we basically have constant digest sizes of just, with a reasonable implementation of this, with just 48 bytes. And sender messages, so this is just the 2 ciphertexts basically, of 256 bytes. So this is independent of the database size. So this is actually very short. Also, the time is very good. So we basically have only single-digit milliseconds to send and receive. Hashing, so basically the part where we compute the digest, of course, that grows with the size of our database because, well, clearly, if we want to commit to a larger database, this needs to grow linearly in the size of the database. So if we go to very large database sizes there, this actually becomes very expensive. So for like 2 to the 18 laconic OT instances, basically we already need 8 minutes to do the hash, but this is something that only needs to be done once and does not need to happen like online. The can just be like pre-computation somewhere. So all of this is fine. The laconic OT has one drawback if you go to very large database sizes, and this is basically the size of the public parameters. So for reasonable database sizes, say 2 to the 14, this is still quite fine. We have like less than 1 megabyte of public parameters. If you want to go to really large database sizes, like 2 to the 31, then you would end up with a ballpark of 100 gigabytes of public parameters, which in many applications may be excessive and not, well, reasonable. But it depends on the application. Maybe in some applications it's also fine, but also 2 to the 31 is a really huge database. And for most applications, something much smaller would probably be fine. Like 2 to the 18 messages is already only 12 megabytes, which is something that you would normally easily be able to deal with. Yeah, and these Like the sizes of our messages are much, much better than previous constructions of laconic OT, like by many orders of magnitude, in fact. The upside of other solutions for laconic OT were that they had smaller public parameters, but it comes at the cost of having like many orders of magnitudes larger messages to be sent as the digest and the sender message. Yeah, with that, I am done and happy to answer any questions you might have.
Is there any question from the audience? I have one question. Your construction uses deterministic KZG commitments?
Sorry, I can't hear it from the.
Your construction uses deterministic KZG commitments?
It's for deterministic KZG commitments.
Is there a motivation for using randomized KZG?
I'm not sure actually if we can modify it.
Even having a stronger notion of security for laconic OT?
Sorry.
Even having a stronger security notion for laconic OT?
I don't know.
Any other question? If not, let's thank Niels again. We move to the second talk, which is an online talk, which should be given by Udai. I don't know if he's online.
Hello everyone, my name is Libert. In this talk, I will show our new work about pairing framed curves with embedding degrees 10 and 14. This is the joint work with De Biao, Tong Hong, Pi Zhenyang, and Chang An Zhao. To start, I give an introduction about pairings and elliptic curves. We use E to denote an elliptic curve of a parameter fp. Then the order of E of fp is equal to p plus 1 minus t. The integer t is a trace of the Frobenius automorphism. If t is not equal to 0, then the curve E is ordinary. In practice, we need the group E of fp as a subgroup with the Nash prime order, such that the DLP in this subgroup is difficult to solve. But this is important for the security of the cryptographic system. The cryptographic pairing is a bilinear and a non-degenerate map that takes elements from G1 and G2 for a third group GT. These three groups have the same Nash prime order. And in detail, the two important groups G1 and G2 are two subgroups of a elliptic curve. And in our work, we need G1 and G2 are different, and there is no efficiently computable anamorphism between them. We usually call it the type-free pairing. The group GT is a subgroup of a finitely fed fp2k. The integer k is the embedding degree of the curve. And if the pairing maps the points P and Q to a value EPQ, then it will maps the points AP and PQ to a value EPQ to A times B. Pairing is a very useful tool to design cryptographic protocols, and in these protocols, it usually needs to perform these four operations. The first one is hashing to G1 and G2. The second one is the group exploitations in the three pairing groups. The third one is the subgroup membership testing. This is mainly used to resist the small subgroup attacks. The next one is pairing computation itself. For a random elliptic curve, its embedding degree is usually large, so we cannot compute pairing on it. For this reason, we have to construct a curve such that its embedding degree is small. In fact, we also wish the value of zone is also small, such that the size of the parameters are not too big. Now, we illustrate how to compute pairing. For most of pairing finite curves, the optimum pairing is the fastest formula. And in this formula, the FMQ is a rational function. It has a zigzag. It has a zigzag of multiplication m at the point q, and a pole of multiplication 1 at the point mq. A pole of multiplication m minus 1 at the identity point, and L denotes the straight line, and mu denotes the vertical line. The notation Ci are integers, such that the sum of Ci times P2I is equal to zigzag modulo R, and the integers Si are determined by the vector C. And for efficiency, which is the fact of the vector C with a small symbol, and the vector, the size of the greatest vector C is only around 1 decade of the size of R. Now we show how to compute the rational function evaluation. We can use the minus algorithm to compute the rational function evaluation. It mainly consists of 2 steps. The first is the minus doubling step, and in this step we need to compute 1 point addition, 1 point doubling, and 2 non-evaluations, 1 field of squaring, and 1 field of multiplication. Under the addition step, we need to compute 1 point addition, 2 non-evaluations, and 1 field multiplication. In fact, there are many other techniques can be used to optimize the minus algorithm. For example, we can use the projective coordinates to compute the point of relation such that the field inversion can be avoided. And moreover, from the trick of denominator elimination, if the embedding degree k is even, then we can include the vertical line evaluation. Now we give some pairing finite curves. In this table, we list the 3 families of pairing finite curves. And they can be parameterized by polynomials. For the Bn and the BLS12 family, they have embedding degree 12, and they are the most popular pairing finite curves. Many protocols use them to implement pairing computation, and the BW13 family has an embedding degree 13. And it may be a nice choice for some special protocols, and we will explain it later. In this table, we list the parameterized for the BN, BLS12, and the BW13 families that can provide the around 128-bit security level. We categorize these curves in 2 types. The first one is the optimistic curve, and the second one is the conservative curve. And if you pursue fast pairing computation, then BLS12281 is the best choice. And this curve now is widely used in the ZK snark. And if you want to balance the efficiency and the security, then the BLS12644 is the best choice. In some cases, pairing finite curves with fast operation in G1 are also attractive, and in these cases, you can choose BW133100. In fact, the performance of pairing computation on the BW1330 is also efficiently. And here we list some advantages and disadvantages for pairing computation and this curve. Firstly, due to the nature of case, the group G2 is defined over a full extension field FP2K. So the point doubling and addition is costly. Secondly, since the embedding degree K is odd prime, the trick of denominator elimination cannot be used. For these 2 reasons, the cost of each minus iteration is really expensive. But on the positive side, the length of the mean loop on this curve can be reduced to around the loop of R over 2 times by K. The question here is, can we find some pairing friendly curves such that the length of the mean loop can be reduced to around the log of R over 2 times pi k? But the trick of the denominator elimination can also be used. And we find that some pairing friendly curves with embedding degrees 10 and 14 meet this condition. Now, we should all mean work. In this table, we list the 5 families of pairing friendly curves with embedding degree 10 and 14. They will have J invariant visible for 17, 28. By using the triple A algorithm, we can find a Schroeder vector that can be used to construct the optimum pairing. From these formulas, we can see that with the request to perform the around 2 times the number of the minus iterations. Now we show how to give a faster formula. There are 2 different efficiently computable anamorphisms on this curve. The first one is the Frobenius map, and the second one is the GLV map. We observe that if we respect the 2 maps and the group G2, then the GLV map is not a part of the Frobenius map. So we can combine the 2 maps together to get a new map. And more interesting, there always exists an integer m such that the action of pi to m after tau corresponds to a scalar z. And based on this observation, we can get a new pairing formula. From the original formula, we can see that the most costly part of the mean loop is to compute as the squared cube of p. First, we can write this function as the product of 2 functions and replace the scalar z by this map. So we can get this new equation. From this equation, we can actually compute the 2 functions in a short mean loop, but we have to pay a penalty for the group exploitation by z in the first function. In order to remove this penalty, we can reach the output of the mean loop for power of P2k minus m such that the exponent of the second function is equal to 1. Then we can combine the group exponentiation by z and the second function evaluation together to save several field squaring. Based on these 2 steps, we can obtain these new pairing formulas. In this algorithm, we show how to compute the mean part of the mean loop for the new pairing formula, and we only need to perform around the number of these minus iterations. Now we consider how to select the set z. Firstly, the set z should guarantee that the size of the FP2K is large enough to resist the text of the variant of NFS. And secondly, to reduce the cost of mean loop, we also wish the sum of the mean loop, mean length, and the Hamming weight of the set z is as small as possible. If not, we also wish the prime p is equal to 1 modulo k, and this condition can ensure that the full extension field FP2K can be easily represented. Based on these restrictions, we find 5 pairing friendly curves that they can reach the 128-bit security level. In the following, we call these curves as the CW curve. Now we consider the operations in G1. Recall that the group G1 is a subgroup of E over FP, and there exists an efficient computable anamorphism on the group G1. For the group exploitation in G1 and the membership testing for G1, it requires to perform around the knockoff R over 2 iterations for the hashing to G1. It consists of hashing to the group E over FP, followed by a cofactor clearing. At the first step, we can obtain a random pointer in E over FP. At the second step, we can map the random pointer into the group G1. Now we show how to perform the cofactor clearing efficiently. By the structure of E over FP, we can first clear the cofactor M1, then we only need to clear the cofactor N1. The naive method is to perform the scalar multiplication directly. Fortunately, we have a faster method to deal with this operation. We observe that the action of the map psi on this group corresponds to a scalar lambda 1. Then, by using the triple A algorithm, we can find the shorter vector A, such that A0 plus A1 times lambda 1 is equal to 0 modulo N1. And the size of this vector is only a half of the size of the A of N1. So we can use the homomorphism A0 plus A1 times tau to clear the cofactor N1. Now we consider the operations in G1 and G2. The group G2 is originally defined over the full extension field. Thanks to the twisted map, all target curves it can be represented as a subgroup of the twisted curve E prime over FP to E, and the integer E is equal to K over R over 2. And there are three homomorphisms and the group G2. The first one is the Frobenius is the GLB map. The second one is the pi prime, and it is induced by the Frobenius map on the original curve. By combining the two maps together, we can get a new map psi. If we restrict the map psi on the group G2, then the order of the psi is equal to 2 times k or 3 times k. And by using this, the homomorphism psi, the number of iterations for group exploration and subgroup membership testing can be reduced to around the knockoff R over 2 times phi k. Actually, this method can be also used to speed up cofactor clearing for G2. In the next, we will explain it in detail. Before that, we first give a subgroup Gz prime, and by this definition, we can say that G2 is the subgroup of Gz prime, and by using the Mobius inversion formula, we can determine the order of Gz prime, and give a random point Q in E prime over FP2E. We can map it into the group Gz prime by using the map pi prime plus 1. So, give a random point, we can first map it into the group Gz prime. Then, by the group structure of Gz prime, we can first clear the cofactor M2, and then we clear the cofactor N2. And in this subgroup, we set it, and we can find that the action of the psi and this group corresponds to a scalar lambda 2. Then, similar as the case of G1, we can use triple A algorithm to find a shorter vector A, such that the sum of AI times lambda 2 to I is equal to 0 modulo N2. Then we can use this homomorphism to clear the cofactor N2. And for the operations in GT, for example, for the group exploration in GT and the subgroup membership testing for GT. Where need to perform the local overfactor iterations, and it should be noted that the inversion in GT is almost free, and the squaring in GT is slightly faster than the squaring in FT2K. Now we have considered what operations on our target curve. And finally, using the radical library, we implement this operation on the two curves. And the results show that the BW13 is faster than the BW10 for all operations. And compared to this particular curve, BW13 is also interesting. For example, for the group exploration in G1 and GT, BW13 is faster than BL12 and BN. And for pairing combination, we find that BW13 is only slower than BW12. We have uploaded our code in the GitHub, and we can find this thing. And if you have any questions, feel free to contact me with this email. Thank you for your attention.
Thanks you. Any question? If there is no question, let's thank you again, and let's thank all the speakers of the session.